Hello everybody, I'm Benjamin Gaume and I will present my work from CT scan to a cold treatment, a 3D digital twin of the human type, carried out with Mr. Teissier, Mr. Michaux and Professor Quemener of the Thermal and Energy team of the Laboratory of Mechanical Energetics of Évry in France. First, I will cover the introduction on the context of this work, especially the origin of the project. Next, we will look at the theoretical framework focusing on Ben's bio-heat equation. We will then move to the methodology. The first section will be dedicated to validation and results. Before concluding, we will present an extension of this model to a full leg. Finally, we will finish with a conclusion summarizing the contribution and challenges of this study. So, I will first present the genesis of this project within the Thermal and Energy team. Contacted by the IRBA, Armed Forces Biomedical Research Institute, we began a collaboration. This made us aware of the important issue of thermal management in the body. Initially, the project focused on exercise-induced heat stroke during a sustained physical effort, and autonomy is not always maintained. We endeavored on our side toward cold climate condition. Quickly, we sought to develop a digital twin model in thermal physics. The adaptation of the heat equation to human biology is Penn equation. We can write it for any domain omega with the form below. We have inertia term, thermal diffusion, heat production, which could be the metabolic heat production in the domain. And we have the Blood exchange with the term rho C omega W alpha as function of temperature T. For the term at the boundary condition gamma, we find the convection with external environment, the metabolic flux at skin level, exchange with blood, and the evaporation term corresponding to transepidermal water loss. Note that the alpha term here, the term of blood flow, as function of T, is nonlinear and varies strongly with temperature here in the figure. It's taken from Whistler, human temperature control. This equation, this bio-equation, has been integrated in our in-house finite element code coded in CPP. Our first work on an exact geometry was possible thanks to the Biomaps laboratory, which was able to provide us a real CT scan. From the voxel CT scan, we segmented the real geometry into recognizable domain. Two methods were used, ITK snap or Aviso. For our tight geometry, we mainly find full domain, adipose tissue, muscle, femoral bone, and bone marrow. For the segmentation, we were inspired by the workflow of Hélène Buis and al. From the article Automatic Segmentation of Cortical and Trabecular Compartment based on Dual Threshold Technique for In Vivo Micro-CT Bone Analysis. So this workflow allows us to obtain an usable and meshable geometry. Note that, however, if the process is not perfectly executed, we can obtain inclusion inside a certain domain. subsequently leading to an obligation to particularly refine the mesh in these areas unnecessarily, as we can see on this tight cross section where fat appear on the femoral bone. The inclusion here exists, but a fair middle ground must be found. After a sensitivity analysis, we obtained a mesh of 3.6 million of tetrahedra, just for the tight. A model on the geometry, we then sought to validate it against experimental data from literature. Here, experiments by Manwine and Costello. Then we evaluated the impact of morphology. For cold treatment, true scenarios predominate, with time varying according to the experiment. We have cold water immersion and whole body cryotherapy. Here, for the Manwine experiment, for the cold water immersion case, a subject perform a warm-up, then go to a rest zone here, before sitting in a cold bath at 8 degrees for 10 minutes, followed by a time in a restroom for a total time less than 1 hour. For the whole body cryotherapy case, after the warm-up, subject undergo 2 successive drop temperature. So minus 60 degree, then minus 110 degree, then rest. To validate this experiment, the author performed temperature measurement at skin surfaces at different depths of the vastus lateralis, a tight muscle. Through our numerical model, we were able to reconstruct the temperature field here at any moment of the experiment. The figure here represents the post-experiment temperature field with the subtraction of adipose tissue in a part and a part of the muscle for a better visualization. We note an heterogeneity of the temperature field on the muscle. We were also able to virtually recreate the temperature probes on the skin and at 1, 2, 3 cm depths in the muscle. So the interest of a numerical model is to be able to display temperature at any point in space and time of the experiment. Figure A represents the evolution of the skin temperature on the vastus lateralis at the probe level. The experimental data from the literature are in orange. The point is the mean, and the box plot is the standard deviation. Finally, not knowing perfectly the metabolic activity, we choose to bond our simulation with basal metabolism in black, and basal max corresponding to 3.5 times the basal metabolism in blue. We can then plot whole temperature for the full observed point. Here. And we perform the same work for whole body cryotherapy. An important point is comparing the two cold treatments. At the end of the treatment, we can observe the temperature profile along the probe here, and we observe better cooling in the case of cold baths, while avoiding subjecting the skin to cryogenic temperature. Finally, still on a tight portion, after having validated this model, we studied the impact of morphology. Subject 1 has a body fat index of 22%. Subject 2 has a body fat index of 38%. The fat mass then acts by its thickness and thermal conductivity as an insulator, limiting the cooling of the muscle. And in the case of the whole body cryotherapy here, not allowing a real cooling of the muscle as expected here. In our recent studies, we have increased the dimension of the geometry by moving to a complete leg, resuming all the previous steps: CT scan, processing, segmentation, then meshing. To obtain leg geometry, we display here the temperature field for the case of a cold water immersion, still with the subtraction of the adipose tissue, and a part of the muscle for better visualization. Before treatment with physical activity, then just after the cold bath, and finally 10 minutes after treatment. During cold bath treatment, we have cold spots, which depend on the thickness here of the adipose tissue. During the relaxation after treatment, the field uniformizes quickly. So, by comparing with the Manwine study for cold bath case, here we have the same figure as previously, but we have the tight hair and the leg in yellow and purple. So we note a little impact, less than 1 degree of the extension from the thigh to the leg. The leg, due to the surface increase, has a thin effect, slightly decreasing the overall temperature of the leg. To conclude our study, we currently have a model using a real geometry applied to pen equation. This model working with a finite element code, any scenario can be studied. Real geometry gives access to the complete field, being able to take into account the impact of morphology. However, obtaining a geometry is complicated. Numerous processing can be heavy to obtain a realistic and usable geometry without too many inclusion. Adapting to a whole body will raise new point ranging from the management of a large geometry to be realistic. We must have a realistic segmentation of trunk, having numerous organs to be taken into account. And finally, the active model is being refined, among other things, at the blood flow level. Thank you for your attention.